Hello, welcome to this part on adjoint sensitivity analysis. This is the third part of these four videos, and in this third part, I'll be talking about time domain adjoint variable method. The two techniques that we discussed in the previous two parts were mainly focused on frequency domain. We assume that we are simulating a circuit in a certain on one frequency, or we have like a motor or finite element analysis or mode matching analysis or method of moments. All these are narrow band numerical techniques. So they assume that you are doing the simulation only at one frequency. So the sensitivities that you get are all narrow band pretty much. If you want to get the sensitivities at multiple frequencies, you have to do a number of simulations. Here we are going to talk about wideband sensitivity analysis. So our system is in general given by a differential equation of this form: ME double dot plus NE dot plus KE is equal to G. M, N, and K are the system matrices. They are functions of our parameters. Parameters here in this case could be material properties, could be different dimensions, and so on. So this is really a time domain equation. The vector E is the vector of state variables, temporal state variables. This could be the electric field and the time domain at different mesh points at all time steps. They could be the vector of magnetic vector potential. They could be any other interpretation depending on the application, electric and magnetic field, and so on. G is your excitation. So this matrix here is n by n. This is n by n. Maybe I should take this one, but let's call this one here m by m. Let's say that the dimension of the vector E is m, while the number of parameters we have x is n parameters. So x has cardinality n, it has n parameters, while these matrices are m by m, where m is the number of state variables E that we have. Okay, once we know these state variables at every time, then we know the response. In general, G is the vector of excitation. Again, this is a time domain vector. It doesn't change with time. It's a temporal excitation vector. The way we solve this equation is that we usually do an integration with time. We can calculate E as a function of k delta t at every time step. Our objective function is this one here. It's given by an integral of some kernel function psi. This kernel function can have both explicit and implicit dependence on x. So you can have something like this. Maybe I can give an example here. I can write, say, that psi is the integral, say, from 0 up to infinity, whatever the case is here, say e1 squared divided by x2, say, and this is dt. Okay, so what's happening here? I'm integrating E1, which is the first state variable, squaring it. I'm integrating it directly to time. So E1 is a function of x2. It's a function of x1. It's a function of all the parameters. So this kernel, this psi here, has an explicit dependence on x2 because x2 appears explicitly, and at the same time, it's also dependent on x2 through E1. So it's dependent on x1, x2, and all the other parameters through this E1 term. Okay, so just keep this one in mind. This kernel function will have both explicit dependence and implicit dependence. So if I want to differentiate psi here relative to say this x2, I will have to differentiate 1 over x2, which is the explicit part, and then differentiate this term relative to E1, and then differentiate E1 relative to x2, which is the implicit part. The derivation of the adjoint variable method is not really that long, but it requires some manipulations. What you have to do, you have to take the system that we have earlier and differentiate it relative to the parameter xi, and the xi can be any one of our parameters. So I here can be from 1 up to n, where n is the number of parameters. So the equation, the system that we have, which is me double dot plus ne dot plus ke is equal to g, we're going to differentiate both sides relative to xi. And we simply use, we differentiate the first term, keep the second term constant, differentiate the second term, keep the first term constant, and so on. We do it for all of them, okay? We keep the term me double dot, me partial e double dot partial xi plus n partial e dot partial xi plus k partial e partial xi, and move all the other terms to the right hand side, and we call it the ith residue. This is a temporal vector. I have all the word forwarding for you. E is a temporal vector. It's a function of time. Then E dot is a temporal vector. Then E double dot is a temporal vector. Okay? If you change any of the parameters, all these vectors are gonna change for all time. Okay? Very important to remember that these are temporal vectors. They are functions of time, but they are also functions of our parameter. So this one here is really a time dependent vector. This is also a time dependent vector. The ith residue, which is related to the ith parameter, is given by this term. Okay, we will remember these residues because we'll have to calculate them for every parameter xi from I equal 1 up to n. So this is really our equation right now. After we took the derivative, we multiply, we take the dot product of both sides with a vector lambda transpose. Okay, so multiply lambda transpose, lambda transpose, lambda transpose, lambda transpose, and do an integration over the complete simulation time. And then we call the simulation time here Tm. Okay, and what we're gonna do, we're gonna select this vector lambda, which is now an arbitrary temporal vector. It's also a function of time. We're gonna select it such that it can give us useful sensitivity information. You can integrate this term twice by parts. So this will give you relative to time. This give you partial e dot partial xi, and then you get here partial lambda transpose dot partial xi. You can again integrate this one by parts. This gives you partial e partial xi, and here this is going to be differentiated, so you get partial lambda transpose partial xi, and so on. So we're going to do integration by parts twice, and we are going to impose the condition that the vector lambda has zero terminal values and zero terminal derivatives. So we don't impose initial conditions for lambda, we impose final conditions for lambda. So the vector lambda is some vector that's changing with time, okay? And I'm gonna impose that at the end of the simulation, it must have zero value and zero derivative. Okay, just remember this expression here, and I will show you how this one is gonna lead us to very interesting sensitivity information. Okay, we integrated by parts and we imposed boundary the terminal conditions, and many of the terms really cancelled out, and we are left only with this term here. Okay, I was able to take partial e partial xi as a common term of all the non-zero terms that remained. Okay, now we have an objective function. What's our objective function? Our objective function, I'm going to write it here. It's an integral from 0 up to tm psi dt. And the psi is our kernel function. If I want to differentiate f relative to xi, what I will have to do, I have to differentiate psi. Psi could have an explicit dependence on xi, as I explained earlier, or it can have implicit dependence. So you have to differentiate relative to the state variables and then differentiate state variables relative to xi. And this is what I did here. Okay? So this is the explicit dependence. So if you have 1 over x1 as we x2 had earlier, this will give you minus 1 over x2 squared. This is the explicit dependence part. We know that part. This part is known. We can calculate this without any extra simulations. Now you take psi. Psi is a function of our state variables. You differentiate it relative to the vector e, and then you multiply relative derivative of E relative to xi. What we are going to do right now is we have to ask ourselves, what is our target? Our target is to calculate this sensitivity relative to all parameters xi, relative to for all I, okay? So we are gonna equate this integral to this integral. This one has partial E partial xi, which is a function of time. Then if for these two to be equal, then this temporal row vector must be equal to this temporal row vector. Okay? What we are trying to do is we're trying to calculate this integral really here, this implicit sensitivity integral. We are gonna force this one to be equal to this one, okay? And if this one is equal to this one, then I can probably calculate this term using that term, okay? So what we did, we're gonna say we're gonna equate two integrals, one to the other. We're gonna equate this integral here to this integral here. We're gonna force them to be equal to one another, okay? Both of them have partial E partial xi. So I'm gonna enforce that this temporal row vector is equal to this temporal row vector. And this is what I did here. Let's take the transpose of both sides. We end up with this adjoint system. What is this adjoint system? This adjoint system, if M of the original system became M transpose, N of the original system became minus N transpose, K of the original system became K transpose. The excitation here is the derivative of the kernel relative to the state variables, relative to the electric field, relative to the magnetic field. Okay? So this we can solve this adjoint system and calculate lambda at every time if we know this excitation, because all these matrices are known. K, N, and M are known, and they are functions for our parameters. We can get them, and then we can carry out integration, time domain integration. We can solve for lambda. Okay? So what we did here, if I have E and if I have lambda, then I can calculate this integral. This integral, this residue depends on E, and this is lambda, this is our adjoint vector. Then I have the sensitivity of F relative to xi, because this integral is equal to this integral is equal to this integral. Okay? And this is really the core concept in this approach. So what we did, we're able to derive this adjoint variable system or adjoint system, and we have the original system. So this is our original system, this is our adjoint system. Notice we take the transpose of all matrices, but for the matrix N, we also change the sign. The excitation here is a vector called G. The excitation here is the derivative of the kernel relative to your state variables. And this is something we can calculate from the original simulation. Okay? So now if I have the original simulation, I get E. The adjoint simulation, I get lambda. Using E and lambda, I can calculate the residue for each parameter. I can calculate lambda. I have all the sensitivities of my objective function relative to all the parameters. Okay, so these are the core steps. You have the differential equation governing your original system. Carry out time domain integration to calculate E for all time, and E is a long vector. If you have 1 million field component, E will have 1 million component. It's a temporal vector of the electric field at every time step. Once I know E, I can calculate partial psi partial E. For example, in the example I've given you earlier, we said that psi was I think it was E1 squared divided by x2. Okay? Then if you differentiate this term here relative to E, it's only function of E1. Then it's going to give me non-zero component only in the first component, and all the other components will be zero because it's not a function of E2, it's not a function of E3, and so on. So I can calculate this one, but this will require the value of E. So if I differentiate this one, I get 2E1 over x2. I need the value of E, which I get from the original simulation. So once you have E, once you have the vector of your original responses, you can calculate the excitation of the adjoint problem, partial psi partial E. And then you can calculate each residue, because the residues require the vector E and its sensitivities. Okay? As if you go back to the previous slide and take a look at the expression for Ri, you see that these residues require the vector E and their sensitivities. Now, you go and solve the adjoint system. Again, we know the excitation of the adjoint system at every time. We can solve this system with time integration. And then once we have lambda, once we have Ri, we can say that the sensitivity of f relative to xi is equal to the explicit part, which we can calculate. It's not that a problem at all, plus this inner product between the adjoint solution and each residue. So only one adjoint simulation is required, and you have all these sensitivities. Even if you have 1 million parameter, it doesn't matter. We needed only one extra simulation, which is the adjoint simulation. Okay, this is too much theory, so let's take a look at one example. We have this circuit here, and this circuit we are going to be solving it in the time domain. So we write the differential equation governing that circuit. We have here, let's see, 1, 2, 3, 4, 5 parameters. So R, C1, L, C2, and this parameter alpha. This is a voltage controlled current source. So the current source is the current's flowing this way from top to bottom. Okay, and we have these values for these parameters. Our objective function is to calculate is to find our target here really is to find the sensitivity of the energy dissipated in the resistor R. The power, the instantaneous power dissipated across R is V1 minus Vs divided over square divided by R. This is the power. So if you integrate power, you get the total energy. Okay, so this is the expression for the energy that we want to get its sensitivities. This is the kernel. This is the kernel. Notice that the kernel is function of V1, which is one of our state variables, but it's not a function of V2. Okay, and it has also an explicit dependence on R. So if I want to, I have to take this into account when I calculate partial f, partial xi. If xi is equal to r, I must have here minus 1 over r squared. I must include that term in my calculations. Okay? Of course, one other thing I should mention, that if you want to calculate the derivative of psi partial to your e, the vector e, psi is only function of v1, which is the first component. So this is going to give you here 2v1 minus vs divided by r, and there is no derivative here relative to v2, because v2 is not psi is not a function of v2. Okay, so what we're going to be doing here is write differential equation. What's the differential equation? We're going to apply KCL at each node. So the sum of this current plus this current plus this current is equal to 0. The sum of this current plus this current plus this current is equal to 0. This current here is C1 dV1 by dt. This current here is V1 minus Vs over R. This current here is the integration of the voltage V1 minus V2. So we have to differentiate the whole equation a second time. So this becomes C1 second derivative V1 relative to time, and so on. So you do the same here. You say that this current plus this current plus this current is equal to 0. This current is alpha V1. This current is V2, is C2 dV2 by dt. This current will be equal to 1 over L, the integral from minus infinity to t, V2 minus V1 dt. You have, after write the equation, you differentiate both sides to get rid of the integration. So you end up with a second order differential equation. Both the KCL and KCL here is going to end up giving you a second order differential equation after we differentiate once to get rid of the integral coming from the inductor. So this is how the governing equation of the system look like. M multiplying E double dot plus N multiplying E dot plus K multiplying E is equal to G. Okay, this is really our original system. Where did this derivative came from? Remember, we had to differentiate both sides to get rid of the integration coming from the inductor. So this was originally Vs over R, and then after we differentiated, it became 1 over R dVs by dt. Okay, so we know M, we know N, we know K. The vector E here, in this case, the vector that we used in our notation, is nothing but V1 and V2, and this is transpose. Okay, very important to remember that. We have here two state variables, they are V1 and V2. Now, what is the adjoint system? The adjoint system will be M transpose multiplying lambda double dot. We have here two lambdas, lambda 1 and lambda 2, minus N transpose multiplying lambda dot. Okay, so see this positive became negative here, and this N is transposed. So the alpha went from here to here. This is K, and gonna say plus K transpose multiplying lambda. Okay, so this symmetric matrix doesn't change. This is equal to the adjoint excitation. What is the adjoint excitation? It is the derivative of the kernel relative to the state variables, relative to V1 and V2. And as I've shown you in the previous slide, the kernel is not a function of V2, so this term is going to be 0, while this term is equal to this quantity here. Remember, this is a time-dependent quantity, so this G is a temporal excitation, and we can know its value, and we should determine its value from the original simulation here. So once I solve for V1 and V2 at every instant of time. So we now know the original system, we now know the adjoint system. We need also to calculate the residues. Remember, the residues will depend on the derivative of the matrix M relative to all the parameters. But matrix M is only a function of C1 and C2. So it's going to give me 1, 0, 0, 1 and 0, 0, 0, 1, depending on the parameter xi and differentiating with respect to. This is N. N is only a function of R and alpha. So if you differentiate this one relative to, if xi is equal to R, this is going to give me minus 1 over R squared, 0, 0, and 0. If I differentiate relative to alpha, it's going to give me 0, 0, 0, and 1. This K is dependent only on L. So if xi is equal to L, this is going to give me here minus 1 over L squared plus 1 over L squared plus 1 over L squared minus 1 over L squared, and so on. Okay, so very important to remember that when we calculate the residues. So this is the expression for the residues that we started with. Please, if you feel confused about this, stop the video now and go back to the slide where we talked about the residues. We need the derivative of M relative to xi, and xi could be C1, C2, you can see the capacity that we have, could be R, could be L, and so on. So let's consider the first parameter. First parameter is R. First parameter is R. This is the derivative of N relative to R. This is minus 1 over R squared. The term of alpha here will give you 0. And this one here, because G is our excitation, G was, it had this term dVs by dt, and I had R, okay? But the residue had partial G, partial xi. So if xi is R, if my current parameter is R, I have here R in the denominator. So this is going to give me minus 1 over R squared dVs by dt. And this is what I have here exactly. So this is the first residue. This is the residue corresponding to the parameter x1, and the x1 is equal to R. Okay? Now let's talk about second parameter. Parameter is C1. C1, this is the derivative here of M, this minus partial M partial C1 multiplying the second derivative of the vector V. Remember, it was C1, 0, I think it was 0, C2. So when you differentiate relative to C1, you get 1, 0, 0, 0. The same thing happens relative to C2, you end up with this one. Okay, now relative to L, this will give you the derivative of K minus the derivative of K relative to xie, and this is what we have here. Okay, so I differentiated the matrix K relative to the inductance L. I end up with this term here. Okay, and the last one is the derivative relative to alpha. The only term that had alpha is the matrix N. We had here 1 over R, 0, alpha, and 0. So if you differentiate this term relative to alpha, everything here will be 0, but this one will give you 1. So this is what you have here. So these are all temporal vectors. You have to calculate them at every time step and store them in the adjoint simulation. But they require the value v1 and v2 at every time step, their first order derivative at every time step, and their second order derivative at every time step. And all of these are available from the original simulation. And imagine the storage that we need here. Here we have 5 parameters. And if you are running your simulation, the original simulation for 10,000 time steps, so you have to store 50,000 values for these residues. Okay? Actually, let me take this one back. There are 5 residues, but each one is 2 components because this is a vector. This is a vector of 2 components. So I have 10 storages per time step. So if I have 50,000 time step, I have to at every time step store 10 values for R. And this is one of the disadvantages of this approach, is that it may require extensive simulation time. There are ways of getting around that, but these are advanced things, but I'm not going to be discussing them in this video. Okay, so if you carry out the original simulation, and you plot V1 and V2 for the given excitation, you see that this is V1 as a function of time, and this V2 as a function of time, and you can know more information about this example in my book. The corresponding adjoint system, if you solve it, you get this lambda 1 and you get this lambda 2. You can see they're all temporal values. Once you have V1, V2, lambda 1, lambda 2, you can calculate all the residues from the original simulation, and you can calculate the sensitivity relative to all your parameters. We did calculate all these sensitivities. These are the sensitivities here obtained using adjoint method, and this one obtained using center of finite differences. They agree mostly in all the components. There are slight difference in the parameter alpha. Our experience tells us when there is a difference between the adjoint and CFD, this means there is a high degree of nonlinearity. So in this case, even CFD may not be that accurate. Okay, so to assume that the adjoint method is less accurate, CFD may not be quite right here. Our experience shows that when these two deviate from one another, this is a sign that the problem is highly nonlinear relative to that parameter. So the parameter alpha is probably a parameter to which the adjoint, the objective function, has a very high degree of sensitivity. And the rest of the parameters, there are slight differences, but they all agree reasonably well. This one here required only one extra time domain simulation to get the vector lambda at every time step. This one here required 10 more extra time domain simulations because we have here 5 parameters. This approach does not only apply to circuits. We did extend that to numerical electromagnetics. We applied it to the transmission line matrix method. And in the transmission line matrix method, what you do, you fill your computational domain with a grid of transmission lines, and you try to model how the electromagnetic energy is spreading through scattering and the connections in this network of transmission lines. I'm not going to get into the details, but starting from the original simulation of the TLM method, there are derivations. You can look up some of my work on papers on this. You see that this is the adjoint system that we get at the end. This one here is running forward in time. This one is running backward in time with terminal values, as we agreed earlier. But using these two, you can get the sensitivity of really any objective function. And we did apply this method to many objective functions, including S parameters and energy and so on.